Hey everybody, I'm Vish. Welcome to the Transformers Recitation. This is a recitation where we're going to try and understand what the transformer architecture is and how to code it. In terms of theoretical understanding, I'm not really going to go into too much depth. The lectures should have covered that for you. We're going to try and understand how that translates to PyTorch code, how we can go about implementing a transformer for a machine translation task. That's the most straightforward one, the most popular one. On the right, I'm just going to refer to some pieces from the attention is all you need paper to remind you of certain elements as we code this. But the inspiration of coding the transformer is from this paper, as you might all know. It powers almost all large language models today, including GPT, GPT-4. Everything is based on this one fundamental pivotal point, right? In AI history, if you will, 2017, not too long ago, I think. But nonetheless, let's get started. This will cover two parts. I think the first part is me going to be explaining how this is coded, how exactly you code a transformer for a machine translation task, and the second part will be by Johannes. He'll go over a vision transformer and how exactly code for that works as well. So you're going to be getting dual pieces. One is a regular transformer for an NLP task. One is a visual VIT transformer, basically, for a CV-based task, right? So both elements. Hope you guys enjoy. Let's get started here. So as you might already know from the lectures, the model architecture consists of an encoder and a decoder. So we're going to get started trying to implement these pieces, encoder, decoder, positional encoding, and eventually then get to the data set. And we'll finally try to train this model and do some inference, right? We all know that transformers basically eliminate recurrence and use multi-head attention to parallelize computation while giving a notion of ordering or, substitute that element of recurrence with positional encoding so that the model understands the relative positions of inputs, right? Because recurrence is absent. Anyway, this is all regular installations that you need to do. We're going to get started here. We download the multi-30K dataset. That's what we're getting started with. We start with jumping straight to this multi-head attention component, right? The fundamental mechanism here is multi-head self-attention, and you do this parallelly, which is also the optimization that we get with transformers as opposed to recurrence models, which have to do things sequentially, right? So multi-head self-attention is used here, as you might see, in a couple of different ways. You have multi-head self-attention in the encoder, once in the decoder, which is also masked, by the way, and you also have multi-head attention right there, right? So in two places, and then there's a separate multi-head attention component as well. So the self-attention here in the encoder and decoder helps the model basically understand its input embeddings. Right here, in this case, it's text to text, so it's text to the encoder and text to the decoder. But ideally speaking, it might be maybe speech embeddings here and text there, right? It could be for anything. And the multi-head attention portion here, as you might see, this is the cross-attention between the encoder and the decoder, basically helping the decoder understand before it generates its output probabilities, how exactly does its self-attended input embeddings relate to the self-attended embeddings from the encoder, right? So understanding that relation is what helps transformer models really make sense of task from encoder to decoder, right? So we all know it's quite a key value based, right? We have a number of heads. We have the head dimension. The reason why we have the head dimension is because we want to scale the multi-head attention output to ensure that we have stable gradients when training. So you have QKV, you distribute the query tensor, the key tensor, the value tensor across the number of heads. In this case, you could have 8 heads. You do it by the head dimension because head dimension is nothing but the overall dimension of the multi-head self-attention divided by the number of heads. You transpose it and then you do the mat multiplication to get the attention values, right? You multiply the query and key to get the attention values, and you divide it by the square root of the head dimension to ensure stable gradients. If you have a mask, right, which will be the portion in the masked multi-head attention of the decoder, which we'll get to, you use a mask here. Otherwise, you just do a softmax and you get the probabilities that you need for the attention values, and you multiply those probabilities with the values to understand the output from the attention module, right? The output also sometimes passes through a linear layer, right, which is again just a weight matrix. All of these are weight matrix. They're represented by linear layers here. That's essentially it. So that summarizes multi-head attention. It's the same formula that you might have learned in class, right? You can see that it's parallelized here. Instead of doing single scale dot product attention as shown in the diagram on the right, we basically parallelize, or basically have stacks of these single scale dot product attentions and then combine all of it at the very end, right? And that's what we're doing right here when we basically do a matrix multiplication and then kind of concatenate all heads together, and then you get batch size and a specific sequence length, and then the head size, the multi-head attention size. So you split it into parallel computations of x head number of heads, right? In this case, it's num heads number of heads. Then you do the computation in parallel, and then you combine it all at the end, concatenate it, and pass it through a linear layer to get the output, right? Feed forward is what you already know. It's simply a linear layer dropout, right, with an activation. That's all it is. It's a block. It's a simple block where you have two linear layers and a non-linear activation. The output of the first layer increases the dimensionality of the input. Second layer reduces it back, and this expansion and contraction that you have allows the feed-forward module to learn the complicated patterns, right, between the features. And naturally, the nonlinear activation is very key. Without that, you're not really learning anything. So the nonlinear activation in between is important. There's also the dropout element for regularization, as shown. The error to norm, this is to maintain stable gradient flow. You have residual connections and you have layer normalization. So you have one layer norm layer, and then in the forward, you're basically getting a residual. You're adding the residual to the input x, and then you're doing a layer norm. This is also kind of straightforward, and that's what you see here in the add and norm modules. Positional encoding is a key component here. We use sines and cosines, right, because as you might have learned in the lecture, we want to give a unique value for every position so that the model kind of is able to distinguish between position A, B, C, D. And because of this non-repeating periodic nature of sines and cosines, it makes for a good candidate. Although in modern implementations, you might also see that this ends up being a learnable weight matrix. That's also a way to implement positional encoding. You might notice this if you went and read how they implement the Whisper transformer by OpenAI Whisper, which is also an open source GitHub link. You can go and see how they implement a transformer model there to transcribe speech to text. They also have a unique query key value cache implementation, which I think is useful to understand. So if you by any chance want to dive deeper into this, I would recommend going through OpenAI's Whisper model architecture on their repository, open source repository. So you have a tensor of zeros, and this is the formula I think you would have right here. Yeah. Position for 2i, position for 2i plus 1, which is the sine of the position divided by 10,000 to the power 2i by d model, which is the exact same thing we do here. And yeah, basically we add it to the input embedding, right, which perturbs the values of the tokenized input and the embeddings by a certain amount so that the model is able to distinguish what each position is in the model and gain a sense of recurrence, if you will, right? And you have the dropout here for regularization purposes. So the 0 to 2 and the 1 to 2 is what is denoted by 2i and 2i plus 1 for people who are not able to understand that. Position, you distribute this to a specific maximum sequence length. If you're doing this as a learnable weight matrix, you would have that as part of your dimensions. And the division term is what you're seeing here, just 10,000 to the 2i divided by d model, which is why we're doing the exponent. And yeah, that's basically it. We move on to the encoder block. The encoder block, as we saw before in the architecture, right? This is one encoder block. It has a multi-head self-attention. It has an add norm, feed forward, add a norm, right? So you have multi-head self-attention, add norm, feed forward, add norm. Just call these in the same order, right? And yeah, there you go. So that's your encoder block. Becomes pretty simple to understand once you start implementing the individual pieces and go up, which is why block processing and block-based coding is really useful and important. The decoder block, again, has a masked multi-head attention. So why do we want a masked multi-head attention framework? We want it because we want the decoder, right, to get a set, to not be able to get a sense of the future values, right, in or to make it somewhat intuitive. You don't want the decoder access to the entire sequence when you're doing teacher forcing, right? So you want it to do masked attention so that it only attends to the values up until the point, right, where it's trying to predict the next token in the sequence, right? Because we're trying to train this for next token prediction, right? And when you're doing that, at every time step, the model should have access to just all the previous tokens and predictions for that time step. It can't know the future, right? Because if it has access to all the future tokens that it's supposed to be predicting, then that's basically teacher forcing. You're giving it access and you're telling it this is what it's supposed to be, learn to predict this. It's not going to learn patterns very well, right? So instead, this mask makes it such that you're doing a triangular matrix where for every time step, the model has access to only all the time steps leading up to it and not anything afterwards. So the attention basically works only for the values or the embeddings up to that time step and not for any of the embeddings after that time step. So the model is kind of learning patterns in a sequence, if you will, right? It's trying to attend to embeddings only up to that time step and not future time steps. That's what masked multi-head attention is about. So you have multi-head self-attention. Same thing here. You have add a norm, and then you have an encoder-decoder attention. This is the cross-attention between the encoder and decoder. This is important because the encoder outputs need to be used by the decoder, but having an attention module helps the decoder understand what features from the encoder model it has to actually focus on to generate its specific next token, right? If we're having next token prediction is the objective here, right? And you have an add norm after that. You have another position-wise feed forward, as you see here, and then another add norm, and that's it. Just call it in the same order. And then finally, we have the transformer model, right? This is all just abstracted by one NN.transformer in PyTorch, but this is what happens behind the scenes, if you will. You have a source target size, source vocab size, target vocab size, right? This is to initialize the encoder and the decoder, right? The D model is supposed to be the dimension that you have for your transformer throughout, which is what usually going to be constant between the source embedding, the target embedding, which is the input embedding, the output embedding. The positional encoding is also D model. You can have the same dimensions. You can have a max sequence length, and you're going to have dropout. Encoder layers, you initialize this for a certain number of layers, and then a decoder layer for a certain number of layers, and then you finally have your final classification, fully connected layer, right? That's going to make the output probabilities. So we don't have a softmax here because cross-entropy loss takes care of that for us in PyTorch, as you might know from the homework. And now we're at the dataset. The dataset is a multi-30K dataset. We have a tokenizer, which we're using from SpaceC, right? For English and German, we're trying to do English-German translation. And we just have a simple vocab dataset class, right? Vocab class, actually, not dataset class, my bad. We have a vocab class to make sure that we have the right vocab. Yeah, this is just counting frequencies and then filtering out tokens with frequency less than the minimum frequency. We can set a minimum frequency of tokens that we want to ignore. And then finally have a vocab, that we can use, right, to tokenize the data set that we have. So yeah, the vocab size that we have finally here, 10,837, 19,204 in German. We have a translation data set, right? We tokenize using the source vocab and the target vocab for every token when we get a specific sentence pair. And we get the source tokens, we add SOS and EOS as we normally do. And we go ahead and have a collate function that pads the sequences so that all of them are the same length. This is the same principle you follow from homework 3 part 2 and homework 4 part 2, right? And we create the dataset classes, right? We create data loaders, and as you can see here, the plain dataset has an input sequence and an output sequence, right? And you can see here, 2 young white males are outside near many bushes. This is the translation in German. Yeah, so we're going to train it for 20 epochs here. D model is 256. You have 8 attention heads. The numbers is 3 encoder and 3 decoder blocks. Feed forward dimension is 512. Dropout is 0.1. Max sequence length is 150 here. Yeah, I think we're kind of set. You define an optimizer. The GNOME scheduler is what they use in the paper. You can look it up. You can try to understand it. I'm not going to go into too much detail due to lack of time here, but you initialize the transformer and add a W, model the parameters. All of this is standard stuff. You have warm-up steps here for the GNOME scheduler. It is, and yeah, you have cross entropy loss, some label smoothing, right? Helper functions include the mask function, where you generate a triangular matrix so that you mask off. Basically, what you mean is you're making the values beyond that specific time step in a triangular fashion. All of the attention values after that should be 0, so that the model doesn't pay any attention to future tokens after that time step. And that's why we generate a triangular mask right there. And yeah, we have a padding mask and a no feature mask, right? Because you also pad all sequences to maximum sequence length. The attention values should basically be 0 for the padding values as well. You want it to be non-zero only for the values that are actually valid tokens. And yeah, we use the blue score here to evaluate the model. And as you can see here, you create a model summary. You have a very good transformer model with about 16.58 million parameters. Pretty small, but this is just for, letting you guys play around with the toy transformer model. You have train and validate functions. In the train functions, you generate a source mask. The source mask here is simply a padding mask, right? Because you're padding sequences in this for a source. So even though this says no mask here, we're accounting for padding. If you weren't accounting for padding, you were just using sequences without padding, you wouldn't have to worry about a mask here. So yeah, you have a target input and a target output. As you see here, the target input, right, is basically everything up to that last, and then it's the next token after that. That's what you want to predict. So you have a target mask, and it has to be able to predict what that next token is, right? What that output should be. That's your label. So provide the source, target, input, and then based on that, you calculate the loss between the output of the model for that next token and then the actual target output itself. The validation is pretty much the same. And yeah, you have the inference function here as well. And inference, which is important for a transformer, has to be sequential. There are obviously newer methods for this, but which is also one of the downsides of a transformer. Training is really fast, but inference has to happen sequentially, right? It has to happen step by step because you're using every token to predict the next token, right? You're using the set of tokens that you predict for X number of time steps to predict the X plus 1th time steps token for next word prediction. So it has to happen in an autoregressive manner. It can't happen in parallel. It can happen in parallel, although training can happen in parallel. You have some experiments here. You train it for 20 epochs. You get a pretty good blue score from 4.6 to 12.38. And the loss clearly decreases, right? This is just a toy problem. You can not really going to give you the best outputs, but here's an example prediction. A man sings and plays the guitar. This is the ground truth sequence in German, and the machine translated sequences does somewhat of a okayish job, right? Mixes up some of the ordering, but you get the idea. The test blue score is around 26. And that kind of concludes the experiment here that we have for coding a transformer. Hope this notebook is of use to you. If you have any doubts on how exactly some of the pieces in this notebook work, feel free to reach out, make a Piazza post, or comment on the recitation post, and I will be more than glad to help you or clarify. Or if you want me to hold office hours specifically for the transformer model, let me know, and I can hold that as well. I will now give the floor to Johannes, who will take you through the vision transformer. Thank you.
So now we'll be talking about vision transformers. So previously, we have shown that transformers were kind of predominantly used for NLP tasks, such as the one you see on your right for machine translation. And on this paper, kind of inspired from the transformational architecture from NLP, kind of used transformers, a pure transformer without any convolution for vision tasks. As we all know previously, as we've seen in homework 2P2, we have used CNNs for image related tasks because they excel at capturing local features through convolutional operations. However, VIT kind of introduced kind of a novel approach by treating each image as a sequence of fixed size batches, and it leverages self-attention mechanism that's inherent in transformers. And as we all know, transformers have shown kind of a good scalability in handling a large amount of data, and the ability to scale transformers to process a sequence of tokens efficiently kind of motivated researchers to kind of apply it for computer vision tasks. So vision transformers are designed to handle images of varying resolutions without requiring major modification to the architecture, and the patch level processing allowed the model to adapt to different input sizes, offering a high level of flexibility that traditional CNNs may find challenging. So when we come to the significance, traditional architecture for computer vision had a local receptor fields that are kind of limited in capturing long-range dependencies in images, and transformers with self-attention mechanism are well suited for global context and relationship between distance images and sequences, and this has resulted in having kind of good performance on image related tasks such as classifications and other stuff. And you can see the input and the attention it produces on images shown in the slide. And what made it difficult to transition for computer vision tasks is the level of computational requirement if you kind of naively apply pixel to pixel attention. So for instance, if you take an image size of 224 by 224, we're basically making every pixel in the image attend to every other pixel, and that will kind of bring a complexity of O in the square. And this kind of made it infeasible because it required a large kind of computational power as well as memory. So in order a solution for this is for kind of split the image into fixed size patches, and we linearly embed them then we add positional embedding similar to the for transformers for the NLP task, and feed them to the transformer encoder, and we have an extra learnable classification token, and this will kind of classify images similar to other CNNs we've used so far. So each patch is kind of treated as a token, and these patches kind of are then linearly embedded to kind of create a sequence of tokens for the transformers, and the sequence of patches serves as an input for the transformer model. So let's dive deeper and how the kind of patches are created. So the name comes 16 by 16 comes because we are taking an image with a resolution of 16 by 16. So as you can see here is the image, and these images are kind of split into patches. Now we are seeing nine patches, and each image is then fed to the linear projection for linear layer to generate like embedding. And after generating the embedding, we give it to the positional embedding. So as we all know, transformers do not inherently understand the order of the input tokens, as they operate on tokens independently. For natural language processing, this is addressed using like positional embedding. The same context applies here. So positional embedding are added to the patch embedding, and this kind of provides information about the spatial arrangement of the patches, and this allows the model to learn the relationship between the patches and the image. So after having the embedding, we will kind of feed this input to the transformer architecture, and the core of the transformer encode architecture consists of multiple layers, each comprising self-attention mechanism and feed-forward networks. And self-attention allows the model to weigh the importance of different patches when making the prediction for a particular patch, and this ability to capture long-range dependencies is kind of crucial for understanding like global image context. And the transformer processes a sequence of patch embeddings through these layers, enabling to learn complex representation of images. And the other special token we have is a class token, which you see it here. So this class token kind of aggregates information from all the patches and used to as like a representation of the entire image, and this token is then fed to the final classification layer to predict the class label. So on the left side of the graph, we can see the similarity of the positional embeddings. So using similarity methods such as cosine similarity, we can calculate the similarity between the positional embeddings. So the input patches here and the input patch columns here. So using this, we can create a graph and a matrix, and this visualization can help us understand how the model perceives a relationship between the sequence of positions. High similarity like this one kind of shows the importance, while low similarity implies a difference in contribution. And analyzing this structure kind of provides insights to the attention mechanism, allows us to interpret how the model processes spatial information and learns positional relationship. And on the right, we can see how the different heads attend most of the images, and we can see that some of the heads attend like globally and just the lowest layers. As you can see, this is head 1 and it's already attending a higher mean attention distance, and this kind of shows the ability to interpret global information and is a kind of indeed used by the model. And other attention kind of attentions have consistently has small attention distances in the lowest layer, and this highly localized attention is less pronounced in like resonates. And if we go even higher in the network depths, we can see like most of the attention heads kind of attain a greater distance. But if we want to see how like convolutional layers is, usually it's gonna be like this. For like network depths that are much lower, you kind of only have a localized attention, but if you as you kind of grow the depths, you will have a more global attention, similar to the vision transformer. So how did it perform, the vision transformers, compared to other kind of benchmarks? So as you can see, it kind of got kind of a higher image classification accuracy, and it was kind of run for using almost 2500 TPU v3 GPUs. And the difference between these two is the patches, and as we have a greater number of like the resolution of the patch is kind of greater, we will have a lower computational requirement compared to the 14 patches. And as you can see, the 14 patches kind of got like a good result in various dataset benchmarks. And so this slide shows how the transformer model performance compares to the CNN model. So swing transformer is kind of a variant of vision transformer, and both of this have shown like comparable kind of performance in terms of accuracy and scalability. And the convex is kind of a family of pure convex model that was kind of released more recently, and it achieved an accuracy of 87.8% on the ImageNet top 1 accuracy, which outperformed the swing transformer on the cocoa detection and segmentation, and while maintaining the simplicity and efficiency of the standard convex. And while vision transformers kind of have shown a superior performance in image classification, they still struggle with computer vision tasks. On the other hand, convex, while being simpler in design, have kind of demonstrated competitive performance across a range of tasks. So choosing between vision transformers and convex kind of depends on several factors: the tasks that you are using, whether it is image classification, segmentation. One might perform better than the other, and the other things to consider is computational resources, such as vision transformers kind of require more computational resources and training data as well compared to convex. And if you have kind of limited resources, convex might be more a feasible option. And the other thing is the performance. Both models have shown kind of competitive performance on various tasks, and when you consider which model to choose, you may kind of opt for a specific performance mastery for your tasks and choose a model based upon that. And the other thing is scalability. Convex kind of compete favorably with transformers in terms of scalability as well. If you need to scale your model to larger datasets on complex tasks, maybe convex might be a better choice. So this all kind of depends on what specific use cases you are using and what kind of performance you want to get for your tasks. And that's it about vision transformers. Next we'll go through a code that kind of shows how you could write vision transformers from scratch. Let's go right to it. Kind of appended to the list, and then stack the patches are kind of specified in the dimension. And after doing that, the next step is to kind of code up the multi-head attention. This is kind of similar to what we showed you in the motion translation. We just take an input sequence and perform multi-head attention, and this kind of help us to focus on different parts of the input sequence simultaneously, and it consists of linear mapping for the queries, keys, and values, and the output obtained by concatenating in linear transformation. The intended values will have a shape of this, and so we'll specify the number of fits and the size of the dimension of the model, and after that we will kind of get the head dimension. After that we linear map for the queries, keys, and values, and for the input we will input the sequence of the images we get from the linear projection layer. So after, it's kind of similar to what we did for the motion translation. If we apply masking, we can do this as well. And for the vision block, so when we are trying to implement the vision block, we will implement something similar to this image, the transformer encoder, as I'm showing in the right. So first we'll start with the layer norm, then it's followed by the multi-attention head, then the layer norm again, then the multi-layer perceptron. So in the forward we did the forward function as well. It's kind of easy to follow. Then next we will initialize the vision transformer transformer module, and so first we will patch the images, then we pass it to the linear mapper, and after that we get as I mentioned earlier, we have another token which is a class token, and we will add this class token as we will just initialize as a random value first, and we will add the positional embedding, and we will then go to the transformer block, and then finally the multi-layer perceptron, which will be used for the classification of the model. So we'll kind of write the forward function kind of similar to the one shown in the diagram, and there is a residual connection as well that kind of written here, so we should implement that as well. And this is the function for getting the positional embedding, and we will define our hyperparameters. Let me run the code. So we'll run the Apache the vision block, and the module itself, the positional embedding, and this kind of limited for number of 5 epochs. And this is very small transformer model, but if you see the base model, usually it is like 86 million parameter with 12 weights, and you can see the multi-layer perceptron size, hidden size, as well as a layer for the base. And since we are kind of implementing for the image dataset, I think this will be enough. Then this is our training loop, and this usually doesn't take that much time to kind of train the model. So after training the model, I was able to get a test accuracy of 75, and this is a diagram that shows the predicted and the target label, and it's kind of similar to the transformer we use for the machine translation. The only difference is we need to patch the images and kind of pass in those sequence of patches to the transformer, and the whole transformer block, the multi-attention block, is kind of similar to what we are going to use in the machine translation. And this is all about the vision transformer, and if you have any questions, please post it on Piazza, and thank you.